All right, welcome everybody to today's live stream for PHYS 413 Quantum Mechanics 1. We've got at least one guest here for the wrong class. You are welcome to stick around if you would like. This is useful information for everybody. Otherwise, our other class, our freshman level class, is this afternoon at 2 p.m. I am really excited about today because we're going to talk about the hydrogen atom. This is one of the biggest accomplishments in quantum mechanics because this is sort of the crowning achievement of everything that we do. It's an exactly solvable problem. It's the hardest problem we will solve in this class. And it's the basis for chemistry. Like everything you studied in chemistry comes from this one solution that we're going to go over today. So let's get right into it. Let me send you in the chat the link to this whiteboard. I think that'll take you directly to this page, but if not, we're on frame 12 if you need to click through that. Otherwise, you can just watch it on the screen here, of course. Basically, what we want to look at is a hydrogen atom. So to remind you of what a hydrogen atom does, we've got a proton in the middle, and we've got an electron going around. So one proton, one electron, the simplest possible atom you can have in the universe. It only gets more complicated from here. Actually, while I'm sending things, let me send a couple of Jupyter Notebook files that we'll be looking at later. If you have Jupyter Notebook, you can go ahead and open it since it takes a minute to open. You can go ahead and open it and download those files, get them open. We'll be looking at those probably about 5-10 minutes. So anyway, this is the hydrogen atom. You have the proton in the middle. You have the electron on the outside. You probably know by now that the mass of the proton is much, much heavier than the mass of the electron. So the proton is basically not going to move. We're going to assume for the sake of simplicity that the proton is mostly stationary. Let's see if I can spell stationary. There we go. I think you spell it the same way as you spell paper. Oh, do they call the paper stationary because it's staying stationary while you write on it? I don't know. That would be an interesting thing to see. Anyway, we're going to assume that this is stationary and that the electron is going around the proton. And so we have to pull in from classical mechanics the potential energy for this thing. Fortunately, that has not changed. I'm getting a confirmation of that idea from chat, so I'm going to assume it's true. Anyway, we use the same potential energy, Coulomb's law here, that you learn in your second semester electricity and magnetism class. We've got an electric constant K. K, for some reason, they prefer to write as 1/4 pi epsilon naught. I've always been a big fan of K instead. It's 9 times 10 to the 9. It's easy to remember. Epsilon naught is some weird number that I can never remember, but I have to look it up. Anyway, there's a constant out in front that takes care of the units. You have the charge of the proton times the charge of the electron. Now, fortunately, those are the same number, E. It's just that one is, squared. There we go. So you have an E times an E gives you an E squared. One is positive and one is negative, so we'll just end up with a negative on the outside here. That negative just means it's going to be attractive. The force here is going to always be attractive between the two. And then you just divide by the distance between the two. So we've got this variable r here. So this problem we're going to be solving in spherical coordinates. So just as a reminder, the way spherical coordinates work, you have three variables, three position coordinates, because you always need three variables to describe something in 3D space. You have r, that's the only distance in the problem. It's the distance from the center of the proton to the center of the electron. You have theta, which if you draw your x, y, and z axes, your z axis is going to point up this way. Theta is the angle that you come down from the z axis. And then phi, if you draw your x and y axes, phi is going to be the angle that goes around in the xy plane. Now, physicists switch those compared with mathematics. Mathematics puts phi up here and theta down here. It really doesn't matter, right? It's literally just a label. Cool. And so classically, what you would do, if this were a classical problem, we would get an ellipse out, right? We would expect this thing to orbit around like an ellipse, because this is the exact same as a gravitational potential energy. You would just replace this K with a capital G. You'd replace these E's with mass of the thing in the middle and mass of the thing on the outside, and this R would stay the same. And it's the 1/r that's really important, right? Everything else is just details, but it's this R that's really important. The fact that U goes like 1/r is kind of the key to this problem. Because the reason that's important is because that means this is the only position coordinate that goes in here. Theta and phi are kind of not invited to the party when it comes to the potential energy, right? Theta and phi are nowhere to be found in the potential energy. What that means is when it comes time to solving the Schrodinger equation, we can actually separate out our wave function, right? So we can take our psi, which is going to be a function of r, theta, and phi, and we can separate it out into a function of r times a function, we're going to call it y, of theta and phi. Right? And so you've probably done this in a differential equations course where you've done separation of variables. And so you can you take one variable, give it one function, you take the other variables, give it another function, because r is going to get the special treatment here. Theta and phi are not even in the potential energy. And so we actually already have the solution to this. This y is going to be the spherical harmonics that we looked at last week. Now, we'll do a little bit of a recap of spherical harmonics in a few minutes, but basically, for these spherical harmonics, I would have to go back to... Yeah. You might remember these spherical harmonics. They have these labels L and M for angular momentum magnitude and angular momentum z component. And they have all these great sine and cosine stuff. They're basically the two-dimensional sines and cosines. Well, that's what we're going to have over here. We're going to have those spherical harmonics. Those functions we looked at last time are going to be the y part. And the only piece that's left, the majority of this chapter is spent trying to solve the Schrodinger equation for capital R. Before we move on to the Schrodinger equation, let's add in a couple more details. You can take this potential energy if you want to study something other than hydrogen. You can multiply it by z, the atomic number. So let's say you want to study helium instead. You would have 2 protons, right? So I would have another proton over here if I were studying, let's do orange for helium. How about that? If I had another proton over here for helium, I would multiply by this z over here. I would multiply by 2 to indicate to me that I've got 2 positive charges in the middle. The question becomes, what do you do with helium's other electron? Well, you've either got to ignore it, because we can't solve the problem with 2 electrons, or you just wave your hands and say, oh, maybe it's ionized helium, as if you're ever going to ionize helium. Let's suppose you rip 1 electron off of helium, and so then you would have 1 electron going around. Then it's an exact solution. Or you can solve the problem numerically, like we love to do. But this is the only thing that might change, is the number of protons that you're working with. For today, I'm just going to assume we're working with hydrogen, because literally everything just scales up with z. Your textbook, Quantum Mechanics by David McIntyre, in chapter 8, it keeps z in everything, so it assumes you might be working with a higher order atom, but we're just going to stick with hydrogen for right now. So z is going to be 1 for everything we do today. Okay, let's take a look at what happens to the Schrodinger equation. Let me move these down. We're going to get to these in a minute. Ignore the equations behind the curtain. There we go. So what'll happen with the Schrodinger equation, so you might remember you've got minus h bar squared over 2m. Now that we're in 3D, you'll have the Laplacian of the wave function plus your potential energy times the wave function is going to equal your energy times your wave function. And so what ends up happening is this potential energy right here we just saw is only a function of r. It doesn't depend on theta and phi. right? So we would call this thing spherically symmetric because I can rotate the problem around theta or phi, and the potential energy looks the same, right? I mean, you don't experience a different gravitational force just because you move somewhere on the Earth, right? It's still gm1m2 over r squared. There's no sines or cosines of angles in there. And so what happens, like I showed you earlier, we take the psi, we separate it into a function of r and a function of theta and phi. And what that means is, when I separate this out, I'm just going to get, for the y term, I'm just going to get this first piece. The second piece is going to go away because I don't have theta and phi in the potential energy. And so that's what gets me the spherical harmonics for this y here. So this thing is just going to be the spherical harmonics that we saw and graphed last time. So literally, we're just taking our new solution r, we're multiplying it by the spherical harmonics, and boom, we're done. We've got psi. When you separate out the r function, this is the equation that you end up with. So you've got the derivative here. So this is your kinetic energy term. Let me get my laser pointer. So this is your kinetic energy term right here, right? This is your derivative, right? So when you go into spherical coordinates, the Laplacian gets really weird really quickly. You get the second derivative like you'd expect, but then you've also got 2 over r times dr times the derivative with respect to r. So this is an extra piece you have to get out from spherical coordinates. I'll leave it to your Calc 3 or applied math professors to explain where that comes from. Basically, you see this derived once, you never have to do it again. And then the next piece is everything else. So we've got our energy here, right? That's our energy factor over here. You've got the Coulomb potential right here. There's E squared, there's K, and there's 1 over R, right? It's this 1 over R that's really driving the problem. Everything else would be the same no matter what kind of potential energy you had. It's this one term that makes it the hydrogen atom and not any other problem. And over here you have an angular momentum term, which is related to the y. You might remember that y is labeled in terms of the angular momentum L and the angular momentum z component m. That's what comes in here, is just this L times L plus 1. You might remember that as the eigenvalue for L squared. So these y's are eigenstates of the angular momentum operator. And so this is just your angular momentum eigenvalue. And so this is what we call the centrifugal term, because this is the term that brings in conservation of angular momentum, which is the thing that keeps the orbiting thing from falling into the thing in the center, right? Right. So for example, the Earth is constantly being attracted toward the sun, and yet we don't fall into the sun. And the reason for that is this conservation of angular momentum. So you've actually got these two competing forces in the potential energy. You've got the electrostatic force, the force that is actually there, and you have this pseudo force, which we sometimes call centrifugal force. That's where that unfortunate name comes into society. We can go into more about that later if you want. But this is the piece that keeps it from falling in, right? Because you've got this negative charge being attracted to this positive charge. Why doesn't it just smack down into the positive charge and they glue together? Well, because of conservation of angular momentum. Once this thing is orbiting, conservation of angular momentum is going to keep it from falling inward. So you really have two competing pieces here. Something goes like 1 over r, something goes like negative 1 over r squared. And so since these two are competing, there's kind of a sweet spot equilibrium. And that equilibrium is basically where the atom is going to, where the electron is going to try to orbit around. Now I say orbit, we know now that we can't really talk about the electron orbiting. We have to talk about the probability density. And that's where these spherical harmonics are going to come in handy, because they're going to help us paint the picture for the probability density. Now, this is a solvable equation, but it's not a very helpful equation, right? There's a lot of stuff going on here. There's this 2 times the mass over h bar squared. This mu that's going to show up here, this is called the reduced mass. It's a combination of the electron mass and the proton mass. You can approximate it as the electron mass, but you can also find it in your textbook as the reduced mass. You don't have to worry too much about what it is. It's just the mass of the electron that goes in here. So I got constants over here. I got a whole lot of constants over here, right? I mean, this 1 over r, this is the only thing that really matters in terms of the differential equation. These are just constants coming along for the ride, and you know how hard it is to keep track of constants along the way. And this whole thing is just a boatload of constants with even some random integers thrown in here. And so what we do, we're going to define a dimensionless version of R. We're going to define a dimensionless or unitless, there we go. We're going to define a dimensionless quantity called rho, and we're going to make that R divided by A. Now this A here, let me give myself a little box. Am I going to be able to fit this in here? I think I can fit this. Ooh, I can fit this in here if I shrink this down just a little bit. There we go. This A here is what we call the Bohr radius. Okay. This is going to be the characteristic length scale of this problem. It's got a few pieces to it. It's basically taking all of these constants and lumping them together. So I have a 4 pi. I can write a better pi than that. 4 pi epsilon naught. I have an h bar squared. That's going to get rid of the h bar squared here and here. And then we're going to divide by mu times z times e squared. So you're literally taking all of these constants and you're combining them in such a way here that create a length. So if you take all the units from here, if you take the whatever units epsilon naught has, the angular momentum units of h bar, the mass here, and the electric charge squared here, you end up with units of length. So this is the Bohr radius. This is the radius that you get if you just kind of naively assume that the electron is a wave going around the proton, and you try to fit a standing wave around her. In other words, you take the circumference and unravel it, and you try to fit a standing wave into that circumference. That would be the radius of the first circle that you could make, right? You would get out these quantized energy levels where you can't be everywhere. You can only be at this level or this level or this level. Well, the radius of that first level would be this combination, the Bohr radius. Bohr, it turns out, with this model, got the correct energy levels, but he got the wrong wave function. So the Bohr radius is a celebration of doing things well enough for passing. Hey children, how are you? We've got a little halfling invasion on the stream today. Say hi, kids. All right, they're waving at the microphone. So anyway, you have this characteristic length scale. So we're going to take our distance here, our center to center distance here, r, the thing that goes in the differential equation. We're going to divide it by a, and that's going to give us a pure number. So you can think of rho as being the r in units of a. So when a row of 1 means r is equal to a. A row of 2 means r is equal to 2 Bohr radii. A row of 3 is equal to means r is 3 Bohr radii, etc., etc. It's just a way of kind of scaling out the units for yourself. And basically what you do, you take this equation and you kind of and you basically replace all your r's with rows, you put in this thing, you apply some chain rule, and you get this out. And while this still has a lot of pieces to it, right, we didn't really lose any terms. While this has a lot of pieces to it, it's a lot cleaner, right? There's no more units on the outside of this bracket. There's no more cluster of stuff over here going along with the 1 over r or with the 1 over r squared. The other piece you have to pick up is this gamma. That is the dimensionless energy. I think I got room to put this in. This is in your textbook if you want to follow along. But gamma here is just the dimensionless energy. And so it's going to be your energy eigenvalue divided by an energy scale of h bar squared over 2 mu a squared. And so that's this is supposed to be a mu here. There we go. Hope you enjoy watching. Hope you enjoy watching me try to write Greek letters. It's quite amusing. So this is your characteristic energy scale or your dimensionless energy scale. And so that just goes in here in place of the E. Oh, excuse me. That needs to be a negative with a square. Negative gamma squared. It's squared for reasons that will become convenient later in the derivation. Basically, you're going to be taking the square root of this thing, so you might as well call this squared, and then you can just write gamma. And then you go through, let me count the pages that this takes up in your textbook. You go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You go through 12 pages. You go through 12 pages in your textbook to get out the answer to this differential equation. I'm not going to repeat that here. I'm not going to make you suffer through my terrible handwriting because honestly, it's one of those things that you just need to read about, know that it exists, know that it works out correctly, and then you just use the results, right? It's not a thing you ever have to repeat. It's a thing you reference if you ever need it to solve another problem. And so you go through 12 pages of derivation to get this out. Basically what you end up with, you need to have the wave function, as always, die off as r approaches infinity. And you know what I'm actually going to do? Let's grab this thing. Let's copy this and paste it on another page here, and then I'll embiggen it. There we go. Now it's embiggened. Let me go background. There we go. And so what you get out, you have to have the wave function die off as it goes out to infinity, right? You have to have the wave function die off. There has to be zero probability of the thing getting infinitely far away. That's what this exponential term does. So you just, in the derivation, you assume that there's an exponential term, and then you're just solving for the rest. So it's going to be e to the negative r times some other stuff, right? So we're going to divide by the characteristic length scale and the energy level n and the charge number, or the atomic number z there. The rest that you need is a polynomial. And so that's where you get these things here. These are I think those are the Laguerre polynomials. I remember seeing that name recently. Let me make sure that that is the name of the thing I am supposed to be referencing. Rydberg, blah, 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 radial wave function. Yeah, Laguerre polynomials. Okay. So these things, you might remember your friends, the Hermit polynomials from the harmonic oscillator. These are a lot like the Hermit polynomials. They're just defined a little bit differently. Basically, it's a thing you look up in a table, or you have Wolfram Alpha or Mathematica spit out for you. It's not a thing you actually have to worry about what it is. It's just a set of polynomials, right? So it's always going to be, so these polynomials are always going to be, rho to the 5th power plus rho to the 4th power plus rho to the 3rd power plus however many powers you need, right? I guess I should start it the other way. There we go. It's always going to be a constant plus a rho to the 1st power plus another rho to the 2nd power plus another rho to the 3rd power, etc., etc., however far up you need to go. The only thing they differ by is these coefficients out in front, right? It's the coefficients who determine the polynomial. And so it's really just those coefficients that you're getting out of the Laguerre polynomial here. And it's the polynomial that gives your wave function its wiggliness, right? So this is the thing that gives your wave function maxima and minima. This is the thing that makes your wave function die down as you approach infinity. And then everything else is constants, right? This thing is just a normalization constant. Oh, excuse me. It's not normalization. It's got an r to the l there. Excuse me. Yeah. So you are multiplying this thing by an r to the l. So you've got a Laguerre polynomial times this thing. Now you might be concerned because this is r to a power, so that's going to grow, but this is going to die down faster, right? Exponential decay always wins out over every other kind of function. And then this piece, this is the piece is just a constant. It's a complicated constant, right? It's got this piece here. It's got some fun combinatorial mathematics going on here. So you got a factorial here and a factorial here. I love factorials over factorials because it seems like they ought to just simplify to something else, but it never quite works out that way. But basically, this thing is a constant. This is a thing you have the computer calculate, right? This is a function you put into your code, and you have the computer figure that out for you. This is basically going to be your radial part of your wave function. So here's the thing you imagine, is that you are trying to look at what psi looks like as a function of r only, right? It's also a function of theta and phi. That's the spherical harmonic parts. But this is the thing that's going to be doing stuff that has maxes and mins and kind of dies down like this. So this is the thing where you're going to get regions where the electron is most likely to be, and regions where the electron is unlikely to be. Regions where it might be located, region where it's definitely not located. Region where it might be located, region where there's a decreasing probability that it'll be located, right? And what you do is you have to kind of imagine these graphs as kind of getting rotated around. I don't know if this is still a popular thing, but we used to have those Christmas decorations where it would be the little corrugated paper, and you would unwrap it in a cylinder, and it would be the kind of like Christmas tree or Santa Claus cutout or something like that. I don't know if those are a thing anymore. But basically, you have to imagine this thing, this graph of R, kind of being, let me get another color, kind of being rotated around in a cylinder, but then also being rotated this way along the theta axis as well. So it's a little difficult to imagine. That's why we're going to go to some Python to help us visualize this. Before we get to that visualization, I do want to pause for any questions so far. So let me give about 45 seconds for that. I will take a hydration break. By the way, your unofficial assignment your unofficial assignment, which I totally can't require you to do, but which you should totally do, is after you finish this lesson, is to go to a chemistry major and just say, do you enjoy the periodic table? And then just say, you're welcome. Because this is our gift to the chemists, is the periodic table. Okay, Peter says, once we see the visuals, it'll make more sense. Yes, it does make much more sense once you can see it. All right, let's take a look at what these things actually look like. First, let's go to this thing we just talked about, the radial wave function. So I'm going to send you in the chat this file. I sent it at the beginning, so if you've already got it downloaded, good for you. If not, here it comes. Here is R of R visualization. There we go. And so this is a code that will graph for you the radial wave function. It comes to us from Angus Nicholson, graphing the radial wave function. Again, this is just this capital R piece. So this is how psi behaves as a function of distance from the proton. So as always, we've got to import a few libraries. We are going to import the Hermit Polynomials because we need those. And we're going to import some plotting utilities. We're going to import an integration routine. I don't know that that's entirely necessary, but we do import it there. First, we've got the Bohr Radius. There's our characteristic length. It doesn't really matter what you call this because we'll be graphing as a scale of that anyway. When you come down here, we're going to get the... This is the radial wave function R. So R here, I should have added this earlier, but R is going to have a label in terms of N and L. So N here is your energy level. Oh goodness, come on, Brian. You can spell better than that. Energy level here. And then L is your angular momentum value. Right? So you see you've got these two subscripts, N and L, and you can see where N and L come into play in the normalization. Also, N comes into play here with how the polynomial gets scaled. So anyway, what we do is first we get the Laguerre polynomial that we need. So we're looking up Laguerre polynomial with indices of n minus L minus 1 and 2 times L plus 1. That matches what we have back over here. N plus L and 2L plus 1. Yeah, there's a 2L plus 1. N minus L minus 1. Okay, I'm guessing the indices are defined differently in the textbook than over here. But then what we do is we multiply this piece here, right? This is r over NA to the nth power. Here's r over NA to the nth power. Here's our e to the negative r over AN. Here's our e to the negative r over AN. It looks like this code chose to ignore the z part. You can add in the z if you want to. And then we have our times 2 over r. Oh, right. This is getting this gets you the Laguerre constant, the coefficient, and this gets you the piece. So what it's actually doing is building the Laguerre polynomial over the course of this loop because it's adding each piece of the polynomial. Anyway, we came here to visualize this thing. So it goes through several functions where you can plot this thing. The neat thing about this is that it's interactive. So when you go to run this, all right, I'm waiting for the thing to come up. I thought it had saved my graph from before. Apparently I was wrong. Anyway, when you go to run this, it's going to ask you which wave functions you want to graph. So during the main function here, it's going to ask you what it is you want to graph, and it'll ask you how many wave functions. Okay, so here it's going to ask me how many wave functions do you want to draw. Let's start with just one. So I'm going to tell it I want to draw one wave function. To what value of r in units of a do you want to plot? So it really doesn't matter what you call a. It's just going to scale in terms of that. Let's go out to, let's say, 10 times a. So again, r is just giving, so you can think of this as your value of rho, right? Because rho is r over a. And then ask what you want to plot. The full wave function, the wave function squared, the wave function times pi r squared, or plot all three. Let's go with the wave function squared. This is the thing we're used to thinking of is the probability density. So let's go with the wave function squared. And then we have to tell it what on our wave function we want. So here it's going to ask for n. The trick is, here we're going to get into the requirements for the integers. N has to be greater than or equal to 1. So let's try a 2. Let's try energy level 2. So we'll go up a little bit in energy. Then it wants us to enter L. Now the trick is L has to be between 0 and n minus 1. This is the piece I always forget, is that it doesn't top out at n, it tops out at n minus 1. Right? And so I have to do something that is less than 2 here. So let's pick 1. You notice we don't care about m because that doesn't enter into the radial wave function. Graph's got an unexpected keyword argument label. Okay, I added that in. I need to take that out. Okay. I was hoping to get these things labeled, but apparently it doesn't like that argument. Okay, so if you are working with this code, please comment that part out. I forgot to test that part. 1 and 10 and wave function squared. And enter the n value. We were going to go with 2 and 1. And here we go. See, and now it's complaining that I have an empty legend. Jeez. Okay. Comment that part out too. So anyway, this is what n equal 2, L equal 1 looks like. You notice it starts out at 0. So there is 0 probability that you will find the electron at the proton, which makes sense, right? I mean, it probably shouldn't be there. We've got a peak over here around 2 times the Bohr radius. It looks just shy of 2. And then it dies down this way. So in other words, if I'm looking for the electron around the proton, this is where it's most likely going to be. Right? And you can kind of tell this thing has an exponential decay, and it's got a polynomial that's really got one peak to it. And that's literally it. We've got a polynomial with a peak, and we've got an exponential decay. I suppose the polynomial's got a minimum over here, just looking at that concavity there. But basically, you can run this as many times as you want to view these wave functions. Let's suppose I want to go with, let's view 3 of them just for fun. Let's go out to 10. And let's suppose I'm interested, let's do the wave function squared. Let's suppose I'm interested in n equals 3. right? Because with n equals 3, I've got several values of L that I could look at, right? I could look at n equals 0. And I could look at n equals 3 and L equals 1. And I could look at n equals 3 and L equals 2. And so here I've got all three of these. So all three of these wave functions will give you the same energy, right? Because I put in an n of 3 for each of them, n equals 3 for all of these. And I have put in an L that's different, right? L can go from -2 up to, L can go from 0 up to 2. So these are all the possible n equal 3 states. And look at how different they are, right? This one, I believe this one looks like it's the L equals 0. That's why I wish it would give me a legend. It starts out up high, and so I do have a probability of getting down into the proton. And then I've got a minimum down here and a new peak up here, and then it exponentially dies down. My next one looks like it's going to be the green one, is my n equals 1 state, starts out at 0 and makes a slow rise up here. So I'm most likely to find it around r equals 6 times the Bohr radius. And then the last one, the L equals, what would that be, 2, has this peak here and then comes slowly down. It looks kind of like the last one we saw. And even though these look very differently, they've all got the same energy level. Because remember, the energy level depends only on n, right? Your total energy for the electron depends only on n. So even though these have such wildly different shapes, they've all got the same energy level. Okay? So this is a look at what the wave function looks like as a function of r. So this is saying you're going out from the proton in a specific direction. You're keeping theta and phi fixed, and you're just looking at the wave function versus r. Now, what you have to imagine is that you're taking this thing and you're rotating around and making it a function of both theta and phi. That's where this second code comes in. Let me get you the link to this one. Link, 3D visualization. This is one that I spent probably about 3 hours on Monday morning clutching together because I was surprised when I searched for Python visualization 3D hydrogen wave function. I didn't find anything. I found some things that would show you the radial function, or I found some things that would give you the full 3D function in a weird external viewer. I didn't find anything that would do it all in Jupyter Notebook. If there is something out there, please let me know in the comments because I would love to see. But basically, so this is the full-fledged hydrogen wave function, right? NLN. You might even remember these labels from chemistry class. We have your energy level, your angular momentum, and your angular momentum z component. This is now a full-fledged function of the position vector, r, theta, and phi. And it's got the two pieces here. It's got our capital R, the thing we were just looking at, and we've got the spherical harmonics that we looked at last time. By the way, it might go without saying, but these two L's are the same. What you can do in this code is you can set the quantum numbers that you want. You can set n, L, and m, and it will spit out, we'll take a look at how it works in a second, it will spit out for you a visualization of the wave function. So this is a 3D wave function of, what is this? This is 211. So this is actually one of the ones we just looked at. So if you go back over here, this is mimicking our green one here. The way it works is I've got several surface plots embedded in each other. So you can think of these as like Russian dolls stacked inside of each other, where each shell represents a different R value, right? Because R is how far out you are from the proton. So imagine the proton is on the inside there. These shells represent where the electron might be. Now, of course, this is all filled in. These shells are just there for visualization purposes. The red indicates a high probability, and the blue indicates a low probability. So you notice a few things. First, you notice we got the same general shape of the spherical harmonics that we had last time, right? Where we've got the YLM gives you a bulge here in the middle, and then it dips in at the top and at the bottom. But what it also does, because I have these shells, it allows you to see how the probability dies down as you get farther away from the proton. So this inner shell is a lot brighter than the outer shell, right? This outer shell, you don't see any red or white. It's mostly blue. The inner shell, you see a lot of blue and white. showing that it's more likely to be there. And so what you have here is a combination of both. Oops, did not mean to open that. Excuse me. I gotta keep my finger off of the right mouse button. What you get here is both the radial function, and you get theta and you get phi all in one visualization. Now you can't rotate it. I do wish you could rotate it. I haven't figured out how to make that happen in Matplotlib yet. But let me just show you how this works. So you set all your parameters here. This is all the stuff that you need to run this. You can specify what your range of R needs to be. It will freak out if you set R minimum equal to 0, so I just made it very, very small. All right. Here you tell it how many shells you want. Here you tell it how many points you want in each grid for theta and for phi. And then here you specify your quantum numbers in L and M. Here it defines the radial part of the wave function. This is exactly what we looked at last time. I copied and pasted it in. Here we calculate the psi squared, and you notice it's just going to be the R function squared times the modulus of the spherical harmonic square. This is the same special function we worked with last time. They gave us the spherical harmonics. So literally, we're just taking the thing we learned today and multiplying it by the thing we learned last week, and boom, we have the hydrogen atom. Now, in order to get this grid stuff to work, I had to convert between Cartesian and spherical coordinates. That's all these three lines are. You can find these in any upper-level physics or upper-level math textbook, the conversion between spherical and Cartesian coordinates. It's pretty straightforward stuff. Here we create a list for all of the independent variables. And then here, basically, we go through and we create our set of values. And so we are going to, we're using this F colors option, face colors option, where basically it's creating these shells, and it's and face colors here just means I want you to color it based on the value. And so red gives you the maximum, blue gives you the minimum. And so you can play around with this however you want. You can view whatever quantum numbers you want. Last time over here, we were looking at 3 and 2. That's kind of an interesting looking one because it's got a maximum out here. So let's try putting in n equals 3, L equals 2, and let's try m. Let's leave m equals 1. Let me refresh my memory on what these look like. So let's see. So for spherical harmonics, we're going to get 2, 1. So here's what you have to imagine is, I need a better visual of this. Yeah. There we go. So what you have to imagine is you're taking the y2, 1. So we got y2, 1 here. So I'm getting this caved in hourglass shape. I guess if you rotate it, if you tilt your head, it's butterfly wings. But I get this concave hourglass shape. So that's y2, 1. And I'm mashing that together with R3, 2. That's the orange here. So I'm going to get a maximum somewhere in R, and I'm going to get a maximum somewhere in theta out here. So let's see what happens with this. I'm going to click, I learned recently you can click run over here and make sure you are running the cell that you want. As Charlie Bucket said, a million pieces take a long time to put together. So we are nearing, we're at quarter till 1. So after we get this visual out here, and of course every time I have to run it twice to actually get a graph. After we get this visual here, I will turn our attention over to our last homework assignment just to give you a few hints on how you might approach those problems. Let me go ahead and turn over to that page while we wait. That one, there we go. Yep, still running. Oh, and there we go. So this is a different state than we had last time, right? You can see I get that hourglass shape here and here, where it's going to be a maximum here and a maximum here. I forgot to change the range on this in terms of R, because according to this, I'm going to need to go out to at least 5R. Yeah, or 5A. Yeah, I'm going out to 5A there, yeah. And so I can also see that I've got a maximum in the R because I've got these shells are behaving differently as I go outward, right? So you can see the range for it broadening as we go out. And so this is pretty, there are probably other ways to visualize this. There might even be better ways to visualize this. But I think this is pretty helpful. I wish we'd had a visualization like this when I was taking quantum mechanics as a senior. I might have understood the hydrogen atom better. Another thing you can do with this, I don't want to do this today. I'm going to make this for a future Let's Code Physics video. You could also use this to show a superposition state, right? Because each of these states is just one eigenstate. The real wave function is a superposition of them. So you could even take these two and put them together and normalize them to get out a superposition state. So yeah, I think this is pretty neat. I've sent the link to you there in the chat. I've also sent it to my students over email. So like I said, you can play around with these to get an idea of what these things look like. Okay, let's take a look. We've got about 14 minutes left on the clock here. Let's take a look at our last assignment. I'm going to bring that in from my other screen here. So in Chapter 8, so we've been over Chapter 9, we've been over Chapter 7. Chapter 8 is the last thing we've looked at. Let me go ahead and send this to you as well. There's a couple of problems in Chapter 8, 8.4 and 8.5. 8.4 says, show that the wave functions representing 1, 0, 0 and 2, 1, 0 states are orthogonal, right? So this is using all that stuff that we just went over. What this is saying, let's see if I can get my drawing tool here. There we go. Okay. What this is saying is take psi for 1, 0, 0 and psi for 2, 1, 0, right? So remember, this is NLM. This is NLM. So like, for example, psi 1, 0, 0 is going to be R10 times Y 10, and then psi 210 is going to be R21 times Y10. So the psi's get three labels, N, L, and M. The R's have 2 labels, N and L, and the Y's have 2 labels, L and M. So they share the, oops, excuse me, that's supposed to be a 0 here. There we go. So they share the inner one. They share the L, right? These two are the same, and these two are the same. Smiley face. I love quantum mechanics. So those two are always going to be the same. The N will be different and the M will be different, but these middle two are going to be the same. Basically, you're going to take those, and they want you to integrate them and show that they are orthogonal. So we're going to take this integral, psi star psi dx, and we want to show that they are orthogonal, meaning that if they're not the same, that integral needs to give us 0. And this needs to be... oops, that actually is not supposed to be a dx, is it? We're in 3 dimensions now. So I'll remind you the way that integrals, and remind myself, the way that integrals work in 3 dimensions. I should have selected a larger eraser. There we go. So I'll remind us that the way integrals work in 3 dimensions, that you got r squared sine theta d theta d phi dr, and you're integrating this over all of space. So your d theta is going to go from 0 to pi, your phi is going to go from 0 to 2 pi, and your r is going to go from 0 to infinity. And I did not plan this out well in terms of where I'm writing, but this is your spherical integral that you did in Calc 3, right? So you've done this plenty of times in Calc 3, where you have to take the thing you're integrating, your measure is r squared sine theta d phi dr. This is not part of the size. This is the thing you are integrating over. This is part of the measure. This r squared sine theta comes along with the d phi and d theta dr. And then you're integrating over all the space. So theta is going to go from 0 to pi. Phi is going to go from 0 to 2 pi. R is going to go from 0 to infinity. You're going to do all that work and show that the whole thing equals 0, because those wave functions need to be orthogonal, right? So these wild and complicated things here, when you mash them together and integrate, need to come out to be 0. Now, you've got a few options for doing that, right? There's a few ways you can do an integral. You can do it by hand. It will take you a page, maybe a page and a half. You know, scan that, take a picture of it, whatever, type it up, however you want to do it, send that to me. Or you can put these into Wolfram Alpha. You can look these up, program the, or you don't have to program these, just type the wave functions into Wolfram Alpha, set up the integral, and have it spit them out. Or you can use our Python codes, right? Because this is getting you the wave function. Numerical integration is just doing a loop over all of space and adding up all the pieces. So you could then have it print out the integral using your favorite numerical integration technique, you know, Simpson's rule, midpoint rule, trapezoid rule, whatever you want to do. So yeah, like I said, you can do this any one of those ways. 8.5 is the other one that we're going to have you do. And that says, by direct application of the differential operators, verify that the state 321 is an eigenstate of h, L squared, and Lz, and determine the corresponding eigenvalues. So you've got the state psi 321. So again, that's n equals 3, L equals 2, m equals 1. They want you to show that it's an eigenstate of h. So in other words, you have to act on it with h and show that you get out an eigenvalue times the same thing, psi 321. So by the time you get from here over to here, you have to show that it's the same function. Function is not allowed to change. You just spit out an e. Well, how do you do that? Well, you take this h, right? This h is minus h bar squared over 2m del squared plus the potential energy. So your h psi is going to be del squared psi plus v psi, and that all needs to equal this thing over here when you put in this particular psi value, right? And then the same thing with L squared and Lz. So like, for example, L squared on psi gives you some number, psi 321 gives you some number times psi 321, and Lz on psi 321 is going to give you some number times psi 321, because that's really the reason we have three indices on here, right? The reason that we have an n, an L, and an m, and we don't just combine those together into one number, is because this thing is at the same time an eigenstate of Hamiltonian, angular momentum magnitude, and angular momentum z component. It's an eigenstate of all three operators. That is not an easy order to fill, right? That is not an easy feat to accomplish mathematically. But it's why we have all this weird normalization constant stuff and all this weird function and Laguerre polynomial stuff, is so that when you act with h, it spits out an eigenvalue. When you act on it with L squared, it spits out an eigenvalue. When you act on it with Lz, it spits out an eigenvalue. So I've reminded you what the h operator looks like here. The L squared and Lz we talked about last time, right? So last time we talked about, oops, oh, I thought I could get that thing to go around. Oh well. So last time we talked about all of this stuff, right? So your Lz operator is xpy minus ypx. Here's what py and px are. And then your L squared is just this thing squared plus this thing squared plus this thing squared. It takes a little bit of doing, but it's pretty straightforward. Again, you've got a few options with how you complete this. You can do this by hand. You can plug in psi 321. You can do this operator on this operator on this operator on this. That'll take you, I'm going to guess, like 3 pages, a page for h, a page for L squared, and a page for Lz. Or you can, again, put this into Wolfram Alpha. You can tell it what psi is, and then just ask it for these derivatives. Or you can also do it on the code. You can get derivatives via a code, and then just show that you end up with the same function back. I'm going to guess that Wolfram Alpha is the easiest of those options for this one, but I welcome and invite your creativity. But again, basically you're just showing that psi is an eigenstate of all three of these. All right, that brings us to about 5 minutes left of our scheduled time. That is all that I needed to talk to you about today in terms of the hydrogen atom. I want to take our last few minutes to answer any questions you might have. So let me give you a minute to post any questions that you've got there in the chat. We have 2 more scheduled live streams. We have one for April 9th and one for April 15th. What I would like to do with those 2 sessions is do a recap of anything we've talked about that you want to go back over. That could be over the last 3 weeks since we've been online. It could be over the last, it could be over the entire semester. It could be anything that's kind of, outstanding. If you've got an assignment that's outstanding that you need to work on, you can ask a question about that. If you've got this last project or this last assignment that you're working on, it can be one of those. Basically, all I want to do is just, go over anything that's still outstanding for you. You can let me know in the chat, or you can let me know over email what you would like us to talk about. But the other thing I'd like us to do, since we've got a little bit of wiggle room in our time left, I want us to take a look ahead at chapter 15. Because chapter 15 in our textbook is where we get to look at solid state physics. This is what my training is in. This is what my dissertation is on. There is not an assignment associated with chapter 15. This is just a thing that it is good for you to be exposed to as an undergrad. And so I would like to take a look at that with you and just kind of go over what the main pieces are. Again, no assignment required or anything. I'll see if I can whip up a code or find a code to help illustrate it, but otherwise we'll just take a look at it. So like I said, before next Wednesday, do let me know what final questions you have from the course, and I'll be happy. I'm happy to repeat anything, happy to go back over anything, happy to take a look at any particular problems that you want to look at. All right, I see we've only got a couple folks in the live stream, so I'll just, I'm happy to wait out the last few minutes to see if any questions come in. Otherwise, I want to thank you all for your time. Hope you're all healthy and enjoying as much physics as you can, and looking forward to wrapping up this semester with you. Thank you. Take care. Have a great afternoon.